An AI is controlling a physical robot, navigating its environment. It achieved this with absolutely no prior training. Let's get into it. Let's start with a featured paper. Embodied GPT-5.1, Evidence of a World Model, by Roberto Spinelli and Tiago C. Martins from University of Sao Paulo. This paper presents a highly novel and surprising demonstration of a frontier LLM exhibiting emergent embodied intelligence without explicit embodiment training, suggesting a significant leap in understanding LLM capabilities and potential for real-world robotics. Here's a full breakdown.
At the heart of our system is a large language model, specifically GPT-5.1, which acts as the robot's brain. It receives the mission prompt and information from memory to decide what to do, all without any special training for being in a robot's body. To perceive its environment, the robot uses its camera to take a picture after each move. This visual information is then stored in memory, providing the crucial context for the LLM's decisions. Next, after the LLM reasons about the scene, it generates specific instructions from a simple set of commands. These discrete actions, like advance or turn, are then sent to the robot to execute in the physical world. Feeding into this process, we analyze the model's internal monologue, which we represent here as the reasoning step. This allows us to find evidence of an emergent world model, as the system demonstrates spatial awareness and physical understanding to solve the mission.
Up next, our second paper out of 3, Socioeconomic Inference in LLM Medical Triage, Same Symptoms, Different Zip Code by Chi-Han Wang. This paper uncovers a critical and ethically concerning bias in frontier LLMs regarding medical triage based on socioeconomic status, highlighting an urgent and pressing problem that demands immediate attention for responsible AI deployment. Let's break down its key contributions.
To start, we set up our experiment with a consistent patient case, giving each model the exact same set of neurological symptoms. This ensures that any differences we see in their advice are due to the socioeconomic factors we introduce, not the medical ones. Feeding into this, we then varied the patient's socioeconomic status using different kinds of signals. These range from explicit descriptions like their insurance status to more implicit cues like their postcode, which you can see listed under the lowest and highest condition columns. Next, we tested 3 different large language models to see how each one would react to these socioeconomic cues. We measured the spread, or the difference in ER referral rates between the highest and lowest SES conditions, to quantify their bias. Finally, we explored how to fix this problem by giving the models a specific instruction to ignore socioeconomic factors when making their decisions. This allowed us to test whether such a simple prompt-based intervention could effectively reduce the biases we observed. Gemini 3.5 Flash demonstrates a substantial positive pooled gap of plus 11.4 percentage points, indicating strong performance. In contrast, GPT 5.4 Mini shows a much smaller positive gap, and Claude Sonnet 4.6 exhibits negligible or slightly negative performance.
Up next, our third paper out of 3, a Frozen 12B beats frontier models on verified work. 100% accuracy, 0 tokens, bit exact, forever by Tsitsi Skelp from Corbenic AI. This paper presents a highly novel and counterintuitive approach to improving model performance by freezing the LLM and growing a verified memory, offering a path to deterministic, bit-exact, and token-free solutions for solved problem families. Let's break down its key contributions.
Let's start by looking at the lower half of the diagram, which shows our proposed verified reuse regime. Here, a frozen 12B parameter model is paired with a verified memory that stores proven solutions. Feeding into that memory is the deposit process, which happens once for each family of problems. This is where we solve a problem and verify the solution is correct without ever looking at an answer key before storing it. Next, when a new query comes in, the select step uses an exact addressing mechanism to find the right solution in memory. This is what allows us to get a bit exact answer every single time, with 0 tokens generated. While this diagram shows the core logic, this architecture enables a massive working context of over 6 million tokens on a single GPU. This capability isn't explicitly drawn here, but it's a direct result of this efficient memory reuse system.
Those were the top papers. Now let's zoom out. ArXiv received 1,238 new computer science papers across 70 subfields today. Here are the trending areas shaping the field. Zooming out, the day's research clustered into 4 big themes: complex AI systems and evaluation, LLM reliability and efficiency, diverse visual AI applications, predictive modeling and efficiency. The full paper list is in the pinned comment below. That's all for today's ArXiv Computer Science Daily. If you found this helpful, please leave a comment, and subscribe for daily paper summaries. See you tomorrow. Thank you to ArXiv for use of its open access interoperability.